Hi there, everybody. So we are going to talk about the types of reactions. There's only 5 of them, and your job is to learn how to tell them apart. So you're going to figure out the characteristics that you want to look for in lab, essentially, to determine when each of these 5 types of reactions is occurring. So as we go through these, pay attention to the kinds of observations you can make in the lab. So that might be heat. It might be, which you can touch, of course. Unless it's fire. Don't touch fire. Okay, so it might be heat, light. It could be the formation of a solid. You might see bubbles, which indicates that a gas has been formed. Yeah, those are the main criteria. So let's take a look at how we can use those observations to figure out which reactions are occurring at any given time. So first off, we have the sort of listing, the definitions for each of the 5 types of reactions. First, we have combination reactions, which is when 2 or more different things come together to form something new. And so the main sort of hallmark for a combination reaction is that when you write the reactants and the products, there's only one product. There are multiple reactants. On the other hand, a decomposition reaction is exactly the opposite thing. You always have one reactant, and it can form 2 or more products. All right. Single replacement, which is also sometimes called single displacement, is when you have an element as a reactant and a different element as a product. So essentially we take one element and one compound and react them together to get a different element and a different compound. This kind of reaction is also known as a reduction oxidation or redox reaction. They are also single displacement reactions. Then we have double replacement, which is also called double displacement reactions. And in that situation, you're going to have 2 compounds reacting together, usually aqueous. And when they form products, you're going to get 2 new compounds. So that's different from single replacement because in single you have an element and double has just compounds. Combustion reactions are pretty obvious because they have fire as a product. So that's heat and light. For the purposes of this course, we are mostly going to be looking at hydrocarbon combustion, which means carbon and hydrogen together in a compound. And when hydrocarbons combust, they require oxygen. It's not always obvious because typically the oxygen comes from the atmosphere. You don't have to add it into the reaction, it's just around. And of course, you're going to produce fire, which is heat and light, although sometimes fire can be tough to see. It's not always orange flames. Sometimes it can be blue. They are always going to produce water and CO2. So if you see flames, you know what the products are. It's always water and CO2. And you know you have to add oxygen to balance the reaction on the reactant side. So here's my pictorial representation of this process, okay? And so pause the video here and see if you can guess what each picture is supposed to represent. Okay, so if we thought of this in terms of generic chemical symbols, so just we're going to use letters instead of actual chemicals because it could be sort of any combination of things, but if you think of the circle as A and the star as B and the lightning bolt as C, this would be an example where we have 2 reactants forming one product. So that's a combination reaction. Here, on the other hand, we have a heart, and it is forming 2 new materials. This is like a breakup, right? Yeah, maybe. This is supposed to represent a decomposition reaction because we're starting out with one thing and we end up with 2 separate things. This is a nod to my fellow video gamers, right? So here we have the 2 princesses together and, of course, the 2 brothers together. And then, once they meet, they're going to react to form 2 different couples. So this might be something like this. Here's a compound because they're connected to each other. We put a plus sign to indicate that these two separate compounds are indeed separate from each other, right? So different kind of punctuation matters here. A plus B is not the same thing as AB, is what I'm saying. And in the end, we end up with, let's see, D and A together. Should have just said Mario, and yeah, but I won't. And we end up with C and B together. Okay, so that is an example of a double replacement reaction, because essentially the cations in each reaction, so the first letters, are going to switch places. And then we have fireworks, right? So fireworks, of course, they produce fire. So we're going to call this one a combustion reaction. It is important to notice that the actual products from this are water vapor and CO2 vapor plus some other stuff, but we're going to ignore that for the purposes of this class. We're going to assume that combustion is always going to go to completion. So in other words, there's no byproducts. And then last we have down here Minnie and Mickey, so that would be like a compound, plus Goofy, which is all by himself, so that's like an element. And then Mickey and Goofy switch places, so we end up with a new compound, and poor Mickey all by himself. That makes this the single, see, single, Mickey is single, replacement reaction. Okay, so those are like visual ways of understanding how the chemicals come together. Now let's take a look at some possible actual reactions here. So here, of course, we have a cozy little fire, and it's combustion because there's flames. You can also think about your barbecue, right? Your barbecue burns propane. And so this is a way of representing the molecules involved in the combustion of propane. And we can do the same thing with a chemical reaction, just like so. We can also do the same thing with the words. So we're going to practice going between the three different views of reactivity, essentially, right? But in all cases, we know there's going to be heat and light, which is fire. So we're going to classify this one as combustion. Along the bottom of the slide, in each of these examples, you should be writing what it is. And how do you know that it is? So in this case, we have flames. The only reactions that we're going to do with hydrocarbons, that is, again, carbon and hydrogen containing compounds, just carbon and hydrogen, is going to be combustion. So you can watch out for that if you see any carbon. This one's pretty neat. So what he's doing here is he's got a block of CO2, which is dry ice, and he has put a little bit of oil in there, and he put some propane in. So the oil is going to catch, and it's going to cause the CO2 to decompose pretty quickly and produce quite a lot of oxygen. Then the heat from the flame and the oxygen and the magnesium are all going to come together to make this really bright white light. This is the same reaction that occurs in, if you've ever played Call of Duty, it's the same reaction that occurs when you use a flashbang grenade. Magnesium is very, very white, and it will blind you. But what's happening is magnesium and oxygen are coming together to produce magnesium oxide plus light. And so this is an example of a combination reaction. The next one we have here, I want you to watch this. Watch his face. Right there. It's going to loop again here for you. He's combining a catalyst in one of the beakers and hydrogen peroxide in another one. And then already in the cylinder is soap and dye so that we can see what's happening. And so what's happening is it's making water, which you can see come off as steam because this is a really hot reaction. So there's the steam. And you also produce oxygen, which gets trapped by the bubbles. That makes this reaction a decomposition. Now he does add a catalyst, as it turns out. It's Ki. It does not count as part of the reactants or part of the products because it's not consumed. Catalysts are the same in the beginning and the end of the reaction. They just make it happen faster. So hydrogen peroxide does this on its own, We're just adding something to make it happen really quickly. And this is why hydrogen peroxide gets stored in a dark bottle and it tells you to keep it close to room temperature. Okay, so let me explain what's happening here. So this reaction is an interesting one. We're taking iron nails and we put it into a blue solution of copper sulfate. So you can kind of see, they put it against a yellow background so you can see that the solution is colored. It looks green, but it's actually a blue solution on a yellow background. The copper is blue in solution. And what we're seeing here is the formation of the element copper right on top of the iron nails. And the iron is disintegrating and you get just copper after a while. Because the iron becomes iron sulfate, which does not have a color, so we can see the yellow background through the solution. So this one starts with an element and it ends with an element. So we're going to call this one single displacement. Now, it's important to know that this kind of solid, this is called a deposit because it forms on a surface. And that is really different from another kind of solid that can form, which is called a precipitate. So a precipitate looks more like this, okay? So first, the two solutions coming together here are clear and colorless, and then we see this yellow cloud form. And it turns out that that yellow cloud is from the the lead iodide, which is yellow. And so this is called a precipitate. And the difference is that it forms throughout the entire solution, so much so that when you do this in person, frequently people may make a mistake and think it's just two liquids because it looks homogeneous initially. However, you can tell the difference between a homogeneous solution and a heterogeneous mixture by either letting it sit for a little while, and in which case all the solid is going to collect at the bottom, or if you hold it up to the light and you cannot see through it, it is not a solution. It must therefore be heterogeneous. Okay? But it's generally a good idea to let things sit and see if a solid settles out before you make your final observations of your reactions in lab. This reaction has two compounds and two compounds as a product, two different compounds. So we're going to say this is a double displacement or replacement, either one. So this is a precipitate, which again forms throughout the entire solution. This one is a deposit, which only forms on the surface that has the element. And that's one way to tell a single displacement reaction apart from a double displacement reaction. They both can form gases sometimes, so we've got to watch out for that. When a single displacement reaction forms a gas, it's usually hydrogen, H2. When a double displacement reaction forms a gas, it's probably carbon dioxide, and it always comes from having a carbonate ion in the reactant. Okay, because carbonate ions, as it turns out, every time that they react in a double displacement, they will form carbonic acid, which very quickly decomposes into water and CO2. And of course, CO2 is a gas. So if you're starting out with two compounds and you see bubbles, be on the lookout. See if you have carbonate present, because that's probably the cause of your bubbles. Okay. So this is your chance to summarize the observations you've made of these reactions and try to generalize them, as well as really just determine how you're going to tell each one of these apart. So pause the video and try to answer each of these things. So you can tell a decomposition versus a single displacement apart because in a single displacement you're going to have one element plus one compound, whereas a decomp is just going to be one substance, probably a compound, because you can't decompose an element. A composition can be determined from a double displacement based on the products. If you can only make one product, that is going to be a composition reaction. That happens most frequently when the components you're combining are opposite charged. In a double displacement, you're going to have two compounds with positive and minus in each of them. Double versus single is going to be easy because a single has an element and doubles don't. Combustion is also easy because fire. For observations, combustion is fire. Single displacement, you might see bubbles or a deposit form. A single displacement, again, you're going to see a solid or bubbles, which is typically hydrogen gas. This can be confusing for people because sometimes when you pour the liquid into a test tube with like a strip of metal in it, sometimes bubbles will kind of stick to the metal. Try to dislodge those and then observe if you see more bubbles being generated. If so, then that's indication a reaction has happened. But if it's just bubbles from pouring and nothing forms after that, then that would be a negative result. Also, be sure that when you put a metal strip in there, you're scrubbing it really well, because most metals have a layer of oxide on the outside, even if you can't see it, which interferes with that single displacement reaction. A double displacement will have heat if you're forming water. You can't see the formation of water, so don't say that you can observe that. You can observe heat, though. So make sure if it appears like a double displacement doesn't have any reaction happen, that you sort of feel it really well for some heat generation. Sometimes I touch it to my wrist because that's more sensitive than the palm of my hands is. So it might be heat. You might see bubbles form if you have a carbonate. You could get CO2, which is really two types of reactions at once. First, you get the double displacement. And then if the double displacement forms H2CO3, which is carbonic acid, then it will decompose to form CO2 and H2O. And of course, the CO2 is your bubbles. But initially, it will look like the double displacement produces bubbles. So that's what you're going to see. The final criterion for a double displacement reaction to occur is if you see a precipitate that forms. If the solution becomes cloudy, not transparent, then that shows you a reaction has happened. So for doubles, we can expect a precipitate, heat, or a gas, bubbles. A decomposition reaction, generally, you might observe the formation of a gas, so you would see bubbles. You might also observe heat. A combination reaction, kind of similar. In the case of the one example I gave you, there was also heat and light. There is usually heat, but not typically as much as magnesium makes. But you also could observe all sorts of things. It could be a solid that forms, but it would only be one solid, not a mixture, not compound plus compound like you would see in double displacement. Okay, so there's a lot of different criterion for combination reactions. The real thing to look for there is you have a combination reaction when you start out with two different substances that may ionize to have opposite charges. So something with a positive charge combining with a negative charge.